Hello and welcome. This is the second lecture in the Machine Vision Level 3 course, and the title of this lecture is Introduction to Machine Vision. So, if we go straight into the lecture material, you see on the Blackboard, of course, the list of different file sections over here. And actually, course materials, if you click on that one, you should see the two lectures that I put on there, videos that I put on there from last week. You can have a look at those whenever you get a chance. Hopefully you've already had a look at them. But if we go to the lecture notes section, we'll see what's going on with the actual lecture notes. So this is the lecture notes I went through last week. Weed classification using convolutional neural networks. And I put on the poster and the lecture, the actual lecture notes. And this is the actual paper that I presented at that conference. Now this week, what I want to do is go into Introduction to Machine Vision. And there we are with the PowerPoint presentation. So click straight away on that and it should come up. It opens up with this PowerPoint presentation. So I'll go through this a slide at a time, starting from the beginning. So it's a basic introduction to machine vision, what we're talking about here. Now, computer vision versus machine vision, as I might have mentioned before. Computer vision involves image capture and automated image analysis across a wide range of theoretical and practical applications. Machine vision is what we call our lab, the Center for Machine Vision, where we're looking more at systems and making use of the data for industrial processes, for example. As it says here, machine vision particularly refers to the use of computer vision in an industrial or practical application, or processes where it's necessary to execute a certain function or outcome. So you're looking for a stone, in this case, and the function is directed by the vision system. The vision system makes everybody aware that there's a foreign object in the production process there. Now, of course, we can use a software library to identify pre-programmed features, or like templates, if you like, and we can get various actions taking place based on the outcomes from the findings in the system. So looking at this one here, we've got a conveyor belt with some apples coming along it, as we just saw, a camera, and importantly, some kind of illumination, interface to the computer, and then we have a sorting unit. Actually, we're working at the moment on what they call a KTP, which is a knowledge transfer partnership with a company who sell vast numbers of used books. And this is kind of similar to what we're showing in the figure here, in that what we've got is a vision system looking at books, in that case, as they come along a conveyor, and then sorting them into different conditions. It's actually quite important because they sell thousands and thousands every day on Amazon, and the condition is really, really important. It's also quite laborious for humans to do that. So these applications were started off years ago with something simple, like looking for whether an apple was the difference between an apple and a stone. But now it's getting more subtle, and you can use machine vision to determine things which up to now require skilled operators, like the exact condition of a book, for example. So I think a lot of the time what vision is particularly good for is looking for situations where you've got a very repetitive situation, but it's quite important as to get it right. If you're looking at food, for example, and you're looking at foreign bodies in the bottom of a container, that's pretty serious if that's missed, especially glass in a honey container or something like that, or children's foods. It could be very serious consequences if it's missed. And it's also the kind of repetitive task that humans aren't much good at after a while. But vision systems don't get tired, of course. So if you detect there's a problem with an item coming along a conveyor belt, you can then correct it and take action to stop it becoming a really serious problem. This is quite important to food producers because supermarkets sometimes have to pay out a lot of money if certain types of foreign bodies are found in their food. So the basic components then of a vision system are, of course, perhaps the most important is, of course, the imaging device. Usually we're talking about a camera, in which we've got an image sensor and a lens, of course. And then we have to interface the camera to a computer, and there's various ways of doing that, which I'll go into some detail about later on. Lighting is very critically important, but often overlooked as a factor in machine vision applications. The computer, we can't do much without that. In smart cameras, you can actually get a processor built into the camera. And then we need some good software for image processing and feature recognition. And what we're using, of course, in this course is LabVIEW, which is made by a big American corporation called National Instruments. And LabVIEW is used to write a shell, which we'll start off using, called Vision Assistant. You'll be using that very soon if you haven't already had a go with it. So then we've got some lighting here on a conveyor belt, another scenario. So thinking then first about the camera. Now, industrial cameras are similar to domestic digital cameras, the kind of thing you might buy off the internet, but they are industrially hardened and calibrated. So first of all, they're usually in a metal case, and they're reasonably repeatable. So if one goes wrong, you replace it with another, which will be very similar to the first one, sort of calibrated, if you like. Now, the parameters you might be considering, of course, are resolution, how many megapixels. A lot of the time people think you want more and more megapixels, but that means more and more processing power in the case of machine vision. So a lot of the time, for many applications, we may not need to look above, say, 5 megapixels. Frame rate, that depends on the application. For very high speed moving things, you might need fast frame rates. For the photo face rig, the face recognition I mentioned, we had to get a very high frame rate for that. It's quite an expensive camera, about £7,000. Spectral sensitivity, depending on what we're trying to detect. Actually, a lot of the time, monochrome cameras will be sufficient. But sometimes you want color, of course, or sometimes you want certain spectral responses. So if you're going to buy an industrial camera, one thing you're going to ask the manufacturer is, can they show you the spectral response of the camera, which will be sort of sensitivity on the y-axis against wavelength. And you'll see where it peaks, and where it peaks depends on exactly what you're trying to do with the camera. Lens mount, of course, that's surprisingly important. This is a C mount, which is very commonly used in machine vision. The interface method of USB 3 a lot of the time. GigE's, of course, used a lot. Co-express. And camera link has always been a high-spec way of interfacing a camera that's been used over many years, we still use. The thing about camera link, in comparison to, say, USB, is that you need to have a card, or you might call a frame grabber, but it's really a card inserted into the computer to get it interfaced with that. So you're talking about £1,300 just for that, actually. Now, there are, of course, other pixel camera considerations which may not be quite as obvious. Now, sensor size is something which you often don't get quoted by camera suppliers, not domestic camera suppliers anyway, but it's pretty important because the overall quality of the image is something that's really important and something that can be overlooked. So it's more important sometimes to get a really good quality image than it is an image which has got a very, very high resolution. And the larger the sensor size, generally speaking, the better quality of the image. For example, if you buy an expensive digital SLR, then you're going to have a large sensor in the back of it, like 2 inches or more. All these cameras that are used in filmmaking have got very large sensors. A large sensor means you've got larger pixels and you get more light, you get a better signal to noise ratio, generally a better quality image. And of course, resolution and sensor size are related to pixel size. Sensor type, well, traditionally that's meant a choice between TTL electronics, which is like a CCD or charge coupled device, and a CMOS electronics, which produce lower voltage devices and what you might find in miniaturized devices, like in your phone, you're going to have a CMOS. Years ago, CMOS wasn't as good as CCD. They used to be a bit noisy, CMOS, but they've come on so much. I mean, the quality of some of the sensors nowadays in mobile smartphones, as you know, is pretty amazing. And they would generally be CMOS, so it's come on a lot. Bit depth, in the case of a monochrome camera, that would be the number of gray levels, which if you had an 8-bit camera would be 256, which to be honest, a lot of the time is enough for a lot of our industrial applications. Manufacturer is surprisingly interesting and important. Usually chips are quite often made by Sony. They've got quite a good dominance of the sensor market, whereas the rest of the device can sometimes be importing the Sony sensor and then putting it into, say, Jai or Dalsa or Basler or some other well-known make. Generally, we stick with well-known makes from manufacturer. You can get cheaper cameras with companies like Hikvision. We make all the cameras that Tesco use in their surveillance cameras in their supermarkets, for example. And they're one of the biggest camera producers in the world, made in China, but probably the quality isn't quite as good as you get from maybe some of the European or Japanese manufacturers, perhaps. Of course, we've got to choose a lens for a particular machine vision application, and we're looking for a good quality images, so we're looking for a good quality lens. And usually we spend about as much on the lens as we do on the camera, which is typically about 800 to £1,000. And Germans are particularly good at the German manufacturers. Schneider are particularly good with lenses. Got some reasonable Japanese lenses around. You can pay anything between 30 to £600 for the same lens, just better quality optics, I guess. So you want to match the lens to the mount, otherwise you might get effects like vignetting, which is where you get darkening around the outside of the image, like they used to have in Victorian photographs. But you don't want that in a machine vision application. You want to get good uniform illumination. If you've got a bigger sensor, you generally need a bigger mount. So you might F mount and above, maybe for very high quality applications. The state of the art in terms of hardware software with the lens, another thing to think about, of course, is the resolution. And this is usually quantified in terms of something called the modulation transfer function. So we're looking here at the resolution and the optical distortion in present of the lens. Now what I will do is get to you hopefully the STEMMA imaging machine vision handbook at some point. It would be good if I could get that to you. I give that to students normally, and it's got a lot of information about this, about practical considerations in relation to lenses and cameras. And really it's a very, very useful document. On the back cover, it's got test patterns for calibrating lenses, and that's why I mentioned it really. So generally speaking, smaller the pixels, higher the resolution required from the lens. And we're looking in resolution in terms of line pairs per millimeter. So we could have a more expensive camera with larger pixels that requires less demanding optics, that might reduce the overall cost of the application. So when you're thinking about resolving power you require for a given application, you're thinking about the combination of the sensor and the lens, really. And the thing is that there are people at companies like STEMMA Imaging, and we also deal with Scorpion Vision, and we also deal with RAD instruments. And these are all people with tremendous, we've got a good, we've got a good relationship with them. We've bought thousands and thousands of pounds of equipment from them, and they know a lot about imaging and cameras and lenses. And they give us this expertise. They're willing to talk to us a lot, and they will sometimes, suggest combinations of lenses and cameras that will give us particularly good imaging for given applications. One thing to be aware of is that you don't always want to get a very small focal length. Focal length being the distance in the center of the lens to the sensor. Now a shorter focal length lens will have significantly more distortion than one with a longer focal length. You might notice this when you use your camera, your digital camera, whether it's in a smartphone or not, but supposing you're taking an image of the inside of the building, and you might have a beam on the ceiling. You might find that in the beam appears to be curved, even though it's actually obviously straight. This is barrel distortion that occurs with lenses with fairly short focal lengths. An extreme example of such a lens is a fisheye lens that you've seen, where you get tremendous distortion, but a very wide field of view. So barrel distortion is something we want to try and avoid. I mean, you can compensate for it, and in LabVIEW there are, VIs that are routines, subroutines that will try to eliminate barrel distortion for you. But generally speaking, in machine vision, you want to get the best possible quality image you can, rather than try to take an image of some problems and then hopefully overcome them. So generally speaking, we would try to use the longest focal length we can get away with. Often we find that anything below 8 millimeters in terms of focal length might cause you some problems in barrel distortion. You might, of course, if you're taking an image of a scene to send to a friend, it doesn't really matter if you've got a bit of distortion here. But you can imagine that if we're using this in a metrology or measurement application, all this kind of distortion can lead to considerable errors in in the ability of the lens to, to be used to give accurate measurements. If this error is constant, doesn't change, then you do stand a chance of compensating for it. And that's what the LabVIEW thing I mentioned does. Some of these routines just look at the distance from the center of the image to the point in question, because there's more distortion the further away you are from the center of the image. You get more distortion up in the corners. Trouble is that the lens may not be perfect, and that distortion, extent of distortion, may be varying depending on where you are in the field of view. So I developed I put a paper, I'll probably put it onto to Blackboard, but it's a piece of research I did on, correcting power distortion using a neural network, which doesn't have the problem of different distortions in places being a problem. So that's the distortion. Now, the optical configuration. The illumination, of course, is really, really important, and generally speaking, we're trying to avoid changes that occur in the image when the background lighting alters. And by controlling the illumination, and we can control how things appear to the camera. You can see this ring light. This is very commonly used in machine vision nowadays. You have a ring light, or it's basically a ring of a lot of LEDs, and then the camera is looking through the middle of it. The advantage of this is that you get diffuse illumination, so it tends to minimize any kind of specular or mirror type reflections that you get, and are usually a problem when you're trying to do imaging. You don't want these mirror type reflections, especially from the surface of, maybe if you've got something wrapped in cellophane, you might get some nasty sort of highlights on the top of that. And this would help to remove that. There are other ways of removing it, like polarization. I don't know if you're familiar with polarization of light, but light can be polarized in terms of its electromagnetic field, and this can be done in a given plane. And it's the same idea as you have in Polaroid sunglasses. The idea in the Polaroid sunglasses is that the light being reflected off the surface of the water, in the pool say, is polarized somewhat. And by having the Polaroids in the glasses, you're sort of eliminating the polarized light, so you're able to look under the water. And that works to some extent, and it's similar with the highlighting I was talking about, because when light is reflected from, say, plastic cellophane, it will be to some extent polarized. So by combining Polaroid filters, you can sometimes use that to eliminate sort of highlighting, which is causing a problem. Polarization actually is a big area, and Gary's done quite a lot of research, Gary Atkinson in our lab, and we've got a project at the moment which is using polarized light to examine carbon fibers. And it's a big project that's going on, and we're using that and some other techniques to look for errors in the way the carbon fibers are being arranged during manufacture. It's quite an interesting project. So another consideration is, do we want monochrome or color? Well, actually, to be honest, monochrome will be perfectly okay most of the time. Is the object moving? If it is, then we probably want quite a fast shutter speed. Now, if you know anything about SLR cameras, single lens reflex cameras, then you know you've got a shutter speed. You've got a speed of the film, they call it, and the shutter speed. The aperture and the shutter speed are used to give you the correct exposure. It's the same with digital cameras. You can control the aperture in a similar way. The shutter is electronic, but it's similar to, in the way it operates, in the effect it has to the old-fashioned mechanical shutters used to have on cameras years ago. So the sensor is being exposed, is collecting light for a certain fraction of a second. And obviously, if you've got something moving, you want quite a fast shutter speed. All these things nowadays are controllable in software. Years ago, you used to have to push little switches on the cameras to control things like shutter speed, but nowadays you can just do it in software. It's not a problem. What is the nature of the object? Morphology, reflectivity, color. So sometimes the way the object appears depends on what its shape is. That's where the morphology comes in. The reflectivity and the color is something called albedo, really. The actual pigment has an effect on, obviously, what it looks like. We have this technique, which I'm going to explain in more detail later, called photometric stereo, which is what they call a structured light technique. So by carefully controlling the position a number of lights and turning them on and off at certain times in synchronization with the camera, you can capture 3D data from objects. In that way, you can separate the morphology, for example, the texture on the surface, from the actual pigment or color, or what we call the albedo. And it works very well. We've used it for all sorts of applications in a wide range of sectors. And I'll talk about it more. We're using it with the composite, for example, which I just mentioned a minute ago. Which features are of particular interest? And you could argue that what you're trying to do in machine vision a lot of the time is arrange the lighting so that the features of particular interest are in as much contrast as possible compared to the background. You know, they're highlighted compared to the background. They're white light, the background's black, dark, for example. What does the surface life of the light need to be? Well, as long as possible. And of course, nowadays, I talk about lots of different types of light, but nowadays, really, we're looking at LEDs. And of course, the surface life of LEDs is pretty good, tens of thousands of hours. And again, what are environmental considerations? Well, to be honest, we're looking at environmental considerations. We're looking at the efficiency of the light. And nowadays, LEDs are much more efficient than old-fashioned incandescent bulbs. So environmentally, that's a big advantage as well. And there are other advantages of LEDs, which I'll go into a bit later. Illumination considerations. This is a diagram that came from that stereo imaging handbook that I was mentioning. And sometimes in one of the courses I run, I've been running for some years an application where we look at coins and we try to identify, the students differentiate between different coins in terms of their area. But if you're trying to image something like a coin, then you've got to worry about the lighting considerations, really. And the way that you angle the light, as you can see here, the way you angle the light affects the way the coin appears. This is front coaxial illumination, so there's illuminated from the front in the same axis as the camera, using a special arrangement, which is explained in the handbook. Front, bright field, diffuse, yes. Bright field and dark field illumination are standard techniques that are used in machine vision for identifying usually 3D defects like cracks or scratches or things that are very hard to see. And they do it by means of using what we call an extended light source. So, for example, you might use a fluorescent tube, which is an extended light source, and then you look at the reflection of the fluorescent tube on the surface you're examining. And if you look directly at the reflection, then that's what you call bright field illumination. And you might have noticed this when you're looking at things in, say, a fluorescent tube, you're looking at on a shiny surface, you notice that any slight scratches on the surface will appear as dark marks. And that's how bright field illumination works. Dark field illumination is very, very similar, but you look just away from the light source, just off the light source, and then any defects on the surface will appear as white marks because the light's been scattered. And these are standard techniques that are good for a very light scratching on surfaces that's otherwise a bit difficult to see. We used it, for example, one time when we had a project some years ago with European Union money, and the idea was to help out stone producers. In the south of Europe, stone processing, polishing, is a very big industry in Italy and Spain. And at the moment, it's a bit short on technology. It's just all very manual and it's very subjective. We were trying to introduce a system which would help the manufacturers know when there's defects, because the polishing tool, which rotates around, made of diamond, if there's a problem with that, then it can scratch the surface of the stone, which is not acceptable. Natural defects are acceptable, but scratches are not. So we're looking for these circular scratches. In fact, I'll probably go into a bit more detail on that application, because it was a nice project where we published papers and we developed a system and delivered it to a company in Portugal, actually. Coming back to this illumination, of course, the wavelength of light that you're using is very critical. If you want to control the wavelength very precisely, you might use LEDs again, because you get LEDs of a particular wavelength, which you can specify. If you want to use a very, very wide range of wavelengths, you might go back actually to using maybe an incandescent light, because a tungsten filament bulb will produce a continuous spectrum, and then you can just use filters to look at particular parts of it. these lights that you get nowadays, which are LEDs, they don't have the same continuous spectrum. They just have light at particular wavelengths. So when you look at what you think is a white LED, it's just a combination of these different wavelengths that ends up looking white, really, rather than particularly continuous. Object reflectivity, specular means mirror-like. So it can be specular or matte, typically a surface. Illumination control, lights can be changed in intensity or pulsed. Again, this is another big advantage of LEDs and also lasers. You can turn them on and off very quickly and control the lighting very well, which is something you can't really do with incandescent bulbs in the same way. You don't have all the problem with heating as well, which is quite used to be a problem with incandescent bulbs. So 2D and 3D computer vision. 2D computer vision involves analysis of conventional images using digital cameras. It's the kind of thing we're all familiar with all the time. 3D vision employs a richer data set for analysing the world in 3D, from data generated from the 3D cameras and systems. Now, this has benefits. 3D can enable robustness in the presence of lights, shadow changes, object size and shape, and 3D texture analysis. So here with 3D, in this case, we're using laser triangulation. So we're projecting a plane of laser light over the tire, and then by imaging it and looking for distortions in the line, we can measure the tread in 3D. And if you rotate the wheel, of course, we can do this continuously over the whole of the tire. So that's a pretty good technique. And we could, if we're doing that, for example, you see, we could match the filter, we put a filter in front of the camera and match that to the wavelength of the laser we're using there. And in that way, this is what it says here, robustness in the presence of light. This would really help the robustness because changes in background light wouldn't have much of an effect because you're looking through this filter. So that does help, and that was something we do a lot of the time. In 3D techniques, you're generally capturing data from the actual surface. So you're capturing actual range data, which you can convert into surface data for an object. And this doesn't have perspective effects and those kind of effects which you get with cameras as well. So there are a lot of advantages of 3D data capture. And I think in the future, it's going to be a really big area for machine vision. And I would say that the Centre for Machine Vision in the BRL has two main areas of expertise, or two niches. The first is 3D, and we spent the last 20 odd years recovering 3D data from all sorts of complicated objects and unusual surfaces in 3D, and that's had applications in medicine and stone, as I said, and also we did talking about tires, we did wheels, we did a wheel alignment project for a company in India, and what we did there was the student approached me and said his father's running a company and wanted me to do a project. I thought that sounds a bit unlikely, but it turns out he did. And he ended up paying us £100,000 for a system we developed for him, which was to do with non-contact wheel alignment. So, you know, when you go to get your wheels aligned, they usually hang pieces of equipment on the wheels. But with this system, which not works, there's no contact whatsoever. There's just these machine vision towers, and you drive your car in and it's automatically aligned. It took us a lot of work to get that working because you can imagine the precision you need to do that is very, very high. So there's a few techniques we had to do to get that very high alignment precision. But it works and he's selling it now, this chap. So that's a good example of impact. So 3D is definitely a hot area. The other area we have expertise in our lab that we specialize in, the other niche, is deep learning. And I bought lots of computers recently with GPUs built in, and we're doing deep learning using convolutional neural networks, typically. And it's a very, very powerful technique. And we find especially that combining 3D data with deep learning gives us tremendous functionality. So image processing then, what's the difference you might ask between image processing and feature recognition? Well, image processing is the first thing you do. You get your image, remove noise using filtering, which I'll talk about later, and we also get rid of data that's not useful, and we want to highlight relevant data. So we can do things like the mean filter. All that means is going over the whole image with a mask, taking the average of all the pixel intensities and changing the central pixel to that average. So you get rid of speckle noise. but you lose a bit of resolution. It's up sort of softening the image. Edge detection, this is useful because if we're trying to detect the diameter, distance across something, width of something, we don't necessarily want to know, or we don't all want loads of data, you just want to know where the edge is. So we use edge detection. Segmentation, really, you can think of that in terms of highlighting features in the image which are particularly useful for what we're trying to do. So if we started imaging the tops of boxes, and we're trying to measure the size of the box, then we probably want to segment the top of the box, not getting any of the floor or anything else in the image, just the top of the box. Then we start applying edge detection to find the edges of the box. Then we start measuring the dimensions of the box. Feature recognition is where we recognize the position, size, and shape of relevant features. And we can sometimes use a template. And we'll go into this a bit actually in the machine vision assistant tutorial, where we use a bit of template matching. So you have a template in the, you might need this a bit for the assignment as well, actually, a little bit of template matching. So you have the template, and then you look for features such as are in the template in the image to identify, to do feature recognition. Then we can do a bit of classification. This is where you might get your neural network to come in to classify into different things that you've got in the image, different objects that are recognized in the image. Then you get your final result. Now, talking about neural networks, what is a neural network? Good question. A bit of a complicated subject, so I'll probably spend a couple of lectures talking about them. It's basically a pattern recognition technique which is data-driven. Now, it was actually invented by a chap called Rosenblatt in 1958. He called it the perceptron. Unfortunately, he talked to the press. He talked to the New York Times. And they published an article in 1958 about how perceptrons were going to go to the, well, be self-aware, reproduce, go on space exploration. And of course, this set people's expectations extremely high when they realized what could actually be done at the time. It led to a lot of disappointment. So although it was invented in 1958, it didn't really get going as a technique until the 1980s, towards the second half of the 1980s. And then there was a resurgence with neural networks, and people realized that you can use them to recognize or model all sorts of functions. For example, if you were in industry and you're trying to model some behavior or something, like for example, a part being compacted out of powder to make maybe, I don't know if you've heard of powder metallurgy, where you make parts out of metal powders. You've got to compact the powder in a press. The rate at which it moves, it varies non-linearly. You can imagine the powder starts off very compressible, becomes very hard like a solid. This is not unusual in industry. Most of the functions that you experience are actually non-linear. Despite that, most of the modeling that's done in industry, even nowadays, is just linear line fitting. So we need something which can model non-linearity. Now that's what neural networks can do when you combine a couple of hidden layers together. And this is why the breakthrough came in the 1980s, because people thought from 1958 that you couldn't model non-linearity because they were just looking at one hidden layer. They realized in the 80s that if you have more hidden layers, you can model all sorts of non-linearity. And that makes them very useful. The great thing about them is that, as it says there, they're data-driven. They're not prescriptive. They're not assuming that the nonlinearity is a quadratic or an exponential or anything else. They're just using the data to model the nonlinearity. That's where the great power comes in. Firstly, you don't have to put your effort into working out what the function is. And secondly, it'll be more accurate because you're not making this assumption, which is probably unrealistic. But how does the neural network work in a nutshell? Well, I can't explain completely here how it works, but you see there are hidden layers. You see there are links between these are neurons, what they call the neurons, where the neural network comes in. These are neurons in the computer. This is a very crude simulation of the way the human brain works. And there are these links between each of these neurons. Now, each of these links has a multiplier associated with it. In other words, you put a value in, it's multiplied by this value to give the value that's going into the next one. Now, the weight is just a factor, which is used in the multiplication. And that's where the model is stored in the neural network. These weights are modified automatically during training. And depending on what those weights end up being, that's your model. Now, that's why some people don't like them, perhaps, and they haven't caught on very much, because most people like a model in terms of an equation, based on the tradition of Isaac Newton. They don't really like the idea of this model being in the network. It seems a little bit unusual. But it turns out it's very powerful. And although we haven't got an equation, it works very well for modeling. So it's an underutilized and very powerful technique. And deep learning is something like this, but a bit more involved, which I'll explain later in the course. And that really is a powerful technique. I would say it's the most significant breakthrough that there has been in artificial intelligence. So here we go then. The one breakthrough that occurred in the history of neural networks was a thing called backpropagation, which is worth being aware of. So the way it works is that the data is put in the training operation. The data is put in, and an error is there's an error detected, which is the difference between what your output's meant to be according to the data, what it actually is. Okay, so that error is used to modify the weights in a process called backpropagation. It's basically an iterative process where you go backwards and you modify the weights and see what effect it has on the error, and you modify them so as to minimize the error. So the reason it's called, it sounds a bit complicated, but it's actually the most simple type of neural network. Feed forward backpropagation. You feed the data forward, get the answer coming out, whatever it is, and then you look at that answer, look at the error to go do the backpropagation to modify the weights. So that's how training works. And when this was invented, this is where the breakthrough occurred in neural networks. Because people had thought about the idea of networks, but they didn't really get anywhere until they worked out the idea of backpropagation for the training. Deep learning, as I mentioned a minute ago, is a powerful technique. We have more neurons, generally speaking. We need lots of processing power to do it. And you really do need a lot of processing power, but it's fortuitous that GPUs just come out on the market with people involved in gaming, and that's come out at the right time for deep learning, because we can make use of all these GPUs and we can do the training with the GPU. Now, the high computational power is only needed for the training. Once you've trained the CNN, you can consult it quickly and easily. You might say, what does it involve? Well, not surprisingly, being called a convolutional neural network, it involves convolution. I'll explain what convolution is a bit later on. But it's a bit like filtering. You're looking at regions of the image and you're applying a mask. And that's the way it works. So it's a bit like, it's a vision technique, really. I think it's interesting that the main breakthrough that's been in AI is actually based on a machine vision technique, which is convolution. And it's extremely useful for us. We use it for all sorts of solutions to all sorts of industrial problems we're given nowadays. So that's a little bit of background on terms of the first lecture. I think what I'd also draw your attention to is having a look at this other paper which I put onto Blackboard. Now, this is a paper that I presented at a conference in 2018 in Las Vegas, and it's really quite a nice little paper because we did this project looking at the London Underground and looking at 3D face recognition on the London Underground. Now, the reason why we did this, we did it for a company who make the gates you've seen on the Underground. They make them for the world, actually, worldwide. But the problem with conventional 2D face recognition is firstly that, as I say, it doesn't necessarily work very well when there's variations in background light, which you get a lot in this country. And also, any system that exists at the moment, no matter who it's made by, Intel or anybody else, can be fooled, any 2D system, can be fooled just by holding a photograph of somebody else in front of your face. So this spoofing problem is overcome with the 3D, because the 3D recovers the shape of the face in 3D, as well as getting the 2D image of the face. So it's much harder to spoof this system. And you're taking the reliability of face recognition from the current achieved values of about 95% up to near 100%. So that's the great power of it. This, I think, is fairly self-explanatory. I've got myself and Wen Hao and Mel were the people on the paper. I think it should explain what we're trying to do, just what I was talking about a minute ago, really. Gives a little bit of background on what's been done on face recognition. The technique that we used, and that's a photograph of it, is again photometric stereo. This is based originally on a project we had from the EPSRC in 2007, which was called PhotoFace, which we did for an American corporation called General Dynamics. And we built the rig and took it to South Wales, where their offices are. And then this was picked up later on by the company who makes the London Underground to see if we could develop it. And we did develop it, and there was a system we built now operational at their research laboratory in central London. It's actually in Farringdon. The company is Cubic, who make these gates. So this system is operational. It's quite interesting. The idea is that you completely do away with gates. In fact, you would do away with all the narrowness of the system they have at the moment, and rather than all this crowding through these tiny gates, it would just be like going into a supermarket, really. And the system would check people walking through, and it would see whether they bought a ticket. So people have to enroll on the system, and then it looks for people who should be traveling. This is not some kind of surveillance thing for Big Brother or anything like that. It's just a system that would be used by people who want to use it to make their lives easier. So they wouldn't have to worry about messing around with bits of paper and tickets and pins and all the rest of it, cards and so on. So that's photometric stereo. That's like a schematic of how it works there. And this is where we had rigged up in the lab, and that's the apparatus that we had. It's now operational in Farringdon, as I say. And we're picking up that face in 3D. So this shows, this was a dummy we used it with. You can see how we've got this false color image. And what it does is it detects this technique called photometric stereo, allows you to detect what we call the surface normal. So this is a vector which is normal to the surface at each point in the image here. And the color here is really dependent on the angle of this vector. So you can see that over the face, the angle's changing over the face here. So it would be very difficult to spoof this because you couldn't print a fake image of somebody else and then also put it onto a 3D face. It wouldn't be something you could do, really. So sometimes people ask me, what about if you 3D printed a face and carried that through? Well, that wouldn't work because, apart from the fact you have to be crazy if you want to do such a thing, I think. The 3D printed face wouldn't have the 2D patterns on it that a normal face would have. So even that wouldn't work. So it's pretty, I think the reviewer of this paper asked me about that, and I did say that. Actually, it got a lot of good reception at the conference. People were very interested in it, talking about the London Underground. And we did get onto the One Show, as I mentioned there, it was on the One Show in 2018. There was two ladies in Bristol who were apparently mistaken for each other, and they came on the show to see if the system could differentiate between them. And interestingly, when we had it in 2D operation, it couldn't tell the difference. But when we turned the 3D on, it could tell the difference between the two people, which I thought was quite enlightening. Anyway, that's the introduction to machine vision. I will put the video onto, of course, as you know, I'm putting the videos on every week at 9 o'clock on a Monday. You've got the tutorial on the Thursday. We will carry on for a little while with Vision Assistant, so make sure you get into that because you need to use that a bit for the assignment. And then we will, after that, get into LabVIEW, which is a general purpose programming language, which I think you'll enjoy and find quite interesting. So thanks very much. I'll see you soon and keep up the good work.